Okay, so I already shared my whole screen. So we already finished on the bracketing method. So we discussed three methods there. We have the incremental search method, the bisection method, and the pulse position method or the regular palsy method. So the bisection and the regular palsy are almost the same in terms of the algorithm or steps. The only difference is in the determination of the approximate root XR. So that is only the difference between them. Then we go with the second and the open method. So it is stated here that, can you see now my presentation? Yung open methods.
Yes, sir.
Yes, sir.
Okay, so open methods are based on formulas that require only a single starting value of x or two starting values that do not necessarily bracket the root. As such, they sometimes diverge or move away from the true value of the root as the computation progresses. However, when the open methods converge, they usually do so much more quickly than the bracketing methods. So this open methods is there is a tendency that we could not go with the location of the root. So unlike in the bracketing method that it is always converged. So we always arrive with the answer of the problem because we already bracketed the location of the root. While in the open methods, so we will start any point in the x-axis. So with that case, there's a tendency that it should not be diverged based from this discussion. But if it will converge, then comparing to the bracketing method, this method is more faster in convergence. So meaning in terms of the number of iterations, we have a lesser number of iteration in the open methods. So we only discuss two methods here. So the first one is the Newton-Raphson method, and the second is Secant method. In the Newton-Raphson method, we only use one initial value of x, while in the Secant method, we use also two initial value of x, but those initial values of x is not necessary that the root is already bounded in that given interval. So let's try to discuss now this first method. So Newton-Raphson method is the most widely used of all root rotating formulas. Only one initial guess of the root is needed to get the iterative process started to find the root of an equation. Sorry. Newton-Raphson method is based on the principle that if the initial guess of the root of the function f sub x equal to 0 is at xi, then if one draws the tangent to the curve at usually xi of xi f sub xi, that is the point xi plus 1, where the tangent crosses the x-axis, is an improved estimate of the root as shown in the figure below. Okay, so medyo meron siyang kamali yung grammar. Okay, so we have here the figure. So I will draw another here. Okay, so naka PDF kasi, so hindi pwedeng masulatan. So let's try to consider another figure here at the right side so that we can illustrate the procedure for this. So meron tayong y-axis. We have also the x-axis. And maybe we have a function that it has a curve looks like this. So we're going to consider maybe the initial x natin. That is our xi. So at this value of x, meron tayong corresponding value of y. So xi and f sub xi. So we have a point here. So I will use so meron tayong point dito. It is now our xi, f sub xi na point. So we have here, okay? So in the statement there, we're going to draw a line in that point with this tangent, okay? So we're going to draw now a line tangent to this point. So assuming that this line now is already tangent to that point xi, f sub xi, then we're going to extend this straight line that is drawn on that point, which is also tangent in that point, until it will crosses the x-axis. And whatever the crossing of that straight line will give to us the new estimate of the root, and we consider that as our xi plus 1. So that is the next approximate value of the root. Then for the next iteration, we're going to consider again our new xi should be the latest value of xi plus 1. So usually we're going to follow na lang yung mga variables na nakalagay doon sa lecture natin. So we have a point here, okay? So that is xi plus 1, f sub xi plus 1. Then we're going to draw again a line that is tangent to that point. Maliit yun. So we're going to draw again a tangent line here, yung blue na kulay. Then the crossing of that straight line is again our new estimate of the root. So ganun yung ang ginawa dito. So from that point again, or that value of xi plus 1, we have again another point na xi plus 2, f sub xi plus 2. Then we're going to draw again a tangent line until we already met the or meet the given stopping criterion. So makita natin in our illustration that our approximation of the root will approach now the location of the root. It is this one. So this is the root. So it will approach that. So how could we determine the formula, or how could we determine the values of xi plus 1 and xi plus 2 and so on? So we can derive that by using the formula for the slope. So we know that slope is the value at the function at that is f prime xi. Okay, so the value of the first derivative at that value of x, or that is also equal to tangent theta. So meaning cosine over sine over cosine, or simply delta y over delta x. So that is the change of y divided by change of x. So if we're going to consider the first triangle natin, considering initial value of x as xi, and it goes to xi plus 1, So meron tayong triangle dito. So we have a triangle here. This one. So yung change of y natin is equal to f sub xi minus 0. And our change of x is xi minus xi plus 1. So we have now that formula here. Okay, so and then ang gawin lang natin dito is we're going to rearrange the equation and we're going to solve now xi plus 1. So we're going to manipulate that. It's that our xi plus 1 now will become xi minus the ratio between f sub xi and f sub prime xi. And this formula is called now as the Newton-Raphson formula. Maybe one of the disadvantage of this method is we are required to evaluate the derivative, the first derivative of the function. So that is maybe one of the problem na ma-encounter natin later on if we're going to solve problems. Most especially if the functions are not readily evaluated yung derivative niya. So yun ang makikita ko nga one problem here. And later on, we will also see some pitfalls or cases that we have a divergence or we could not solve the problem. If we can solve the problem, it takes a very long solution or more iterations. So ipakita natin lahat yan. So we go with the algorithm of this method. So these steps to apply Newton-Raphson method to find the root of an equation, f sub x equal to 0 are number 1. So evaluate the first derivative of the function using the analytical method. Second, use an initial guess of the root xi. So we can choose any value of x here. So because it is open, so we consider that as our xi. Then to estimate the new value of the root xi plus 1, as the formula xi plus 1 is equal to xi minus f sub xi over f sub prime xi. So yun ang dinerive natin kanina, which is the Newton-Raphson formula. Then number 3, find the absolute relative approximate error. So that is our AA. Using the formula, the absolute value of the relative approximate error should be equal to the absolute value of xi plus 1 minus xi over xi plus 1 multiplied by 100. So yung xi plus 1 is usually the present value or the present approximation. Yung xi is the previous value or previous approximation. So the same pa rin sa formula natin sa relative approximate error. And number 4, compute the absolute relative approximate error with the pre-specified relative error tolerance, ES, that if the absolute value of the relative approximate error is greater than ES, then go back to step number 2. So, we're going to compute again the new value of xi plus 1. So that is step number 2. Else, stop the algorithm. So if we already met the condition that EA is less than or equal to ES, then we will stop the iteration. Also check if the number of iteration has exceeded the maximum number of iterations that is already set in the given problem. So the same function as in the previous methods in the bracketing method. So f sub x equal to e raised by negative x minus x. So again, we use also the same stopping criterion para ma-compare natin the number of iteration sorry, iterations for every methods. So first is we're going to evaluate now the derivative of e raised by negative x minus x. So this function is readily available. We can evaluate directly the derivative because we only use the formula. So the derivative of e raised by negative x is e raised by negative x multiplied by the derivative of the power. And the derivative of the power is negative 1. So we come out that the derivative now, f sub prime x is equal to negative e raised by negative x. Then minus the derivative of x is equal to 1. So ito yung first derivative now of the function f sub x is equal to e raised by negative x minus x. So ito yung sinabi ko kanina na kung mahirap na evaluate yung derivative of a certain function, then we cannot use this method, the Newton-Raphson method. But the next method will answer that problem, the second method. So makita natin mamaya. Then substitute to the Newton-Raphson formula, yung xi plus 1 with the formulas now for the f sub x and f sub prime x. So xi plus 1 is equal to xi minus, in the formula is f sub x over f sub prime x. So we substitute now here, okay? So that is now the formula. Then we go now with the iterations. So starting with an initial guess of xi is equal to 0, this iterative equation can be applied to compute now the following. So we can see here that iteration number 1, the initial value of xi is 0. Then after that, we can compute now the value of xi plus 1. That in this case, we have a value of 0.5. So ipakita ko lang yung computation natin at that value. So xi plus 1 is equal to xi, which is 0, minus e raised by negative 0 minus 0. So that is xi all over negative e raised by negative 0 minus 1. So 0 minus e raised by negative 0 is 1, minus 0 is simply 1. Then negative e raised by negative 0, the result is negative 1 minus 1. So that we have now negative 1 all over negative 2. And this one now is already positive 1/2 or 0.5. So we come out with that new value of xi plus 1. Okay, so if you compute the relative approximate error, the present value is 0.5, the previous value is 0, and we come out with a value of 100% error. Okay, then based from our discussion, the new value of xi now should be the latest value of xi plus 1. So based from our discussion kanina, so this one. So ito yung first value of xi natin. Then we calculate the value of xi plus 1. So that is the first iteration. Then for the next iteration, ito na yung bagong xi natin. Then we have that point. Then, meron naman tayong bagong xi plus 1. Then, for the next iteration, ito na naman yung xi. Then, we can determine again the new value of xi plus 1. So, in that procedure, so ang mangyari dito sa solution natin is our xi now will become 0.5. Then compute again the value of xi plus 1 using the same formula. So i-compute ko pa rin yung value na how could we arrive with 0.566 So this is taken from xi, it is now 0.5 minus e raised by negative 0.5 minus 0.5 all over negative e raised by negative 0.5 minus 1. So if you're going to use your calculator to evaluate that one, we have a result of positive 0.566311. So that is the new value of xi plus 1 under iteration number 2. And if you compute the absolute relative approximate error, the present value is 0.566311 and our previous value is 0.5. So using the formula for the relative approximate error, we have a value of 11.709291%. So hindi pa natin na meet yung condition assuming our stopping criterion is n is equal to 2, such that our ES, the Scarborough equation value should be 0.5%. So we go another iteration, say iteration number 3. The new value of xi should be the latest value of xi plus 1. It is now 0.566311. Then compute again the value of xi plus 1 from the Newton-Raphson formula, just that our x is equal to, or our xi should be 0.5663311, and we arrive a value of 0.567143317. And the value of the absolute relative approximate error is already 0.146, which is already less than 0.5. So meaning that we can stop now at iteration number 3. So we can stop at that and we conclude that the root now is equal to that value, yung merong highlight na green. So 0.5671317, okay? So if the stopping criterion is equal to n is equal to 2. So yung iteration number 4, iteration number 5, so kahit wala na yan. Pero pinakita lang natin dito. Now you can see here that the relative approximate error in absolute value is already very, very small, okay? In iteration number 4, we have already 2.21 times 10 raised by negative 5. So meaning, apat na yung 0, 0.00002 something percent. While the fifth iteration is we have already 12 zeros after the decimal. Okay, so 0.000 up to 509%. So this is a very, very small value. So if we compare in the bisection method, we have only 3 iterations, while in the bisection, we have 7 iterations. By the way, this number of iteration pa rin is, it depends upon the initial value of x. Okay? Because in bisection, we can also reduce the number of iterations by considering a smaller interval between the initial values of x. Also, in the Newton-Raphson method, we can still further reduce the iterations if your initial x should be near to the root. So kung mas malapit yung kinonsider mong value ng xi, you have also lesser number of iterations. So it depends on those conditions also. Kaya in the numerical methods, it encourages that you're going to determine or see the physical appearance of the problem. And one way is by plotting the curve. And from there, you can estimate the location of the root, and it will serve as your basis in the determination of your initial values of x, whether it is on the bracketing or on the open methods. So, yeah, so that is for the Newton-Raphson method. And let's say to discuss also some pitfalls on this method. So, cases where convergence is slow. So, meaning we have many iterations before we can determine the root. So, there are two cases here. Number one is an inflection point such that f so double prime x is equal to 0 occurs in the vicinity of root. So you know now what is inflection point, okay? So that is the part of the curve that it will change its slope, okay? So ipakita natin mamaya. Initial guess encounters near zero slope, or that is f sub prime x equal to 0. So the convergence of Newton-Raphson method depends on the nature of the function and on the accuracy of the initial guess. The only remedy is to have an initial guess that is sufficiently close to the root. So yung sinabi ko kanina, good guesses are usually predicated on the knowledge of the physical problem setting or on the devices such as graphs that provide insight into the behavior of the solution. So I will show you the cases. So the first one is the root is near and the vicinity of an inflection point. So the inflection point is the part of the curve that it changes its curvature. Okay, so makita natin dito. Hindi ko kasi masulatan ito, naka-PDF kasi yan. So I will draw another here. So meron tayong curve na ganito. So usually this is the root. And as you can see here, that the location of the root, the curvature of the curve will change. Okay, so makita natin dito sa left side of the root, the curve is opening upward. Then at the right side is already opening downward. So ganun yung inflection point. So kung saan siya mag-change yung curvature. Okay, so if that is the case, that the root is near on that point, then there is a tendency that we have a long number of more number of iterations. So let's say to illustrate, so gawin ko dito sa drawing ko. So if you consider this one is our initial guess. So in the illustration is 0. So f sub 0. So from this point, xo and f sub xo, we will draw a tangent line. That tangent line should be extended until it will cross the x-axis. So assuming the crossing now is this one, so maybe x1, then we will draw again a tangent line at the point x1 and f sub xi or x1. So it should be somewhere here. So should be looks like this. And so meron tayong another estimate of the root that is x2. So maybe we extend the curve like that. So again, meron na naman tayong another point here, x2 f sub x2. Now you can see that the tendency is we will not go with the location of the root. So we go away the root. So that is the first case natin under the pitfalls of Newton-Raphson method. So there's a tendency that we could not solve the root. If we can solve the root, it takes many iterations before we go that point. So the remedy is we will go with the initial guess of the x to be near at the root. So yun lang ang pinaka-remedy for this. So that is an example now for the first case that the root is within the vicinity of the inflection point. Then another illustration here is and the root or the initial guess is near zero slope or f sub prime x is equal to 0. So yung drawing doon is looks like this. I will draw another. So it should be looks like this. So maybe somewhere here is kung kunin natin yung tangent, assuming na horizontal siya. Kung horizontal yung tangent, meaning we have a zero slope. So kung nagkataon na eksakto siya for a value of x that will give to us a zero slope, then the tangent line will not cross the x-axis. So mga kasanyo, assuming na nakatsambahan natin yung initial guess natin ng x to be the value of x that it comes to zero slope. So ang mangyari is yung line na i-construct natin will not go or it will not cross the x-axis. Yan. Say example, kung hindi naman siya eksakto, say certain na medyo malayo, certain na distance with that. Okay, let's consider another. I-erase ko muna yan. Dami na. Okay, so yun muna. Okay, so let's consider initial x, xo. So assuming ito yung xo natin. So meron siyang tangent dito na ganito. And then so this is our x1. Then meron naman tayong point dito. It goes again there. And then another point here. Then again it goes here. So hindi tayo makalayo dito. So ganun ang mangyayari if that is the case. So instead now we go approaching the root. So ito yung location ng root. So dito lang tayo mag iterate. Hindi siya papasok dito sa vicinity of the root. So if you're going to consider an initial guess, say xo at this point, then so hindi natin makita yung curve natin nila. So maybe it looks like that. So medyo lalapit dito sa location ng root. So that is the solution. So another illustration, yung third figure. So makita pa rin natin na we started at x equal to xo. It goes to x1. and it goes to x2. So instead na it will go with the vicinity of the root, it go away with those location of the roots. Another, so inflection point pa rin, yung pang-apat. So, without knowing the physical appearance of the root and or the problem, and maybe you already encountered this situation that the initial point is near zero slope, or the location of the root is within the vicinity of the inflection point, then what will happen is you have a more iterations. So, and or tendency that it will not converge. Okay, so that is for the Newton-Raphson method. Um, ang i-memorize lang natin dito is yung formula for the Newton-Raphson formula na xi plus 1 is equal to xi minus f sub xi over f sub prime xi. So, yan lang. Then, maliit lang naman yung algorithm. So, yung kung tingnan natin dito sa example natin, we consider initial value of x as 0. Kinompute natin yung xi plus 1 using the formula. Then, ang bagong value ng xi should be the latest value of xi plus 1. Compute again the new value of xi plus 1, and so on. And we're going to monitor also the value of the relative approximate error so that we know what iteration we're going to stop in the calculation. And so, ganun lang yung algorithm. So, madali, okay? In the next method, and the second method, is to answer now the problem regarding and the evaluation of the first derivative of the function. So, in the statement here that a potential problem in implementing the Newton-Raphson method is the evaluation of the derivative. Although this is not inconvenient for polynomials and many other functions, there are certain functions whose derivatives may be extremely difficult or inconvenient to evaluate. So, usually, yung mga transcendental equations or the non-algebraic equations, medyo mahirap na evaluate yung mga derivative. Unlike in polynomials, that we only use the power formula to evaluate the derivative. So for these cases, the derivative can be approximated by a backward finite divided difference. This backward finite divided difference is one formula under the numerical differentiation na i-discuss natin almost last part of our subject. So the formula looks like this. F sub prime xi should be approximately equal to f sub xi minus 1 minus f sub xi all over xi minus 1 minus xi. So this approximation can be substituted into the Newton-Raphson formula. So xi plus 1 should be equal to xi minus f sub. Okay, so bale ang ginawa dito is hindi niya pinakita lahat. So xi plus 1 should be equal to xi minus, isuot ko muna yung formula, f sub xi, then f sub prime xi. So xi minus f sub xi, then substitute natin yung formula ng f sub prime xi from the backward finite divided difference. It is now equal to f sub xi minus 1 minus f sub xi all over xi minus 1 minus xi. So it simplifies that yung xi minus 1 minus xi will go to the numerator to be multiplied now to f sub xi. So yun ang ginawa dito. And then we have now the second formula. We already eliminated the evaluation of the derivative. So the second formula requires two initial estimates of x. So meron tayong initial values of x as xi and xi minus 1. So it should be illustrated like this. So, okay, again, I will draw another para sulatan ko. So we have still the x-axis, y-axis, the curve of the function. And so we consider two initial values of x. So maybe xi, and meron tayong xi minus 1. So meron tayong dalawang points dito. So not necessary that this initial values of x will bound the location of the root. So makita natin dito na ang root natin is on this point. So yung in between xi minus 1 and xi is outside yung location ng root. Then ang gawin natin, yung dalawang points natin dito, we connect by straight line. And that is the approximate slope. And we're going to extend this until it will intersect the x-axis. And this is our new estimate of the root xi plus 1. Then after that, for the next iteration, okay, so bali, kung we go with the algorithm, so ang first algorithm natin is we're going to consider xi and xi minus 1. Then, using the formula for the second formula, we can locate now xi plus 1. Then, for the next iteration, we go now with this two values here. Okay, so ito na yung bagong value ng this is now our new xi, and this is now our new value of xi minus 1. So we will connect again these 2 points here, so that we have again new estimate for the root xi plus 1. So ganun ang ginawa. So almost the same as on the Newton-Raphson. The only difference here is we already consider two initial values of x. So we have still 10 minutes. As I to discuss the algorithm. So almost the same as in the Newton-Raphson. So begin with any 2 points. So xi and xi minus 1. Calculate xi plus 1 using the second method formula. So we have the formula here. Replace xi with xi minus 1. So yung drawing ko kanina, replace xi minus 1 with xi plus 1 and repeat from step 2 until convergence is reached. Or if we already meet the stopping criterion, then we will stop the iteration. So use the two most recently generated points in subsequent iteration. So example pa rin, the same. So we consider the initial guess to be 0 and 1. Then compute for the values for f sub xi and f sub xi minus 1 because we need these values in the computation of xi plus 1. So based from the formula, we need those values to come out with 0.61269984. Then makita natin yung xi, ang new value niya is already 1. Okay? So from the discussion, replace xi with the value of xi minus 1, whatever the latest value. Ganun din sa xi minus 1, ang new value niya should be the latest value of xi plus 1. So parang in the arrangement na dito sa lecture natin, mag-move yung mga values natin going to the left. So to the left na po ba? Then after that, compute again the values of the functions for the new values of xi and xi minus 1 to come out with the new value of xi plus 1. Because in the second iteration, ang value niya is 0.563, 8 something. At this iteration, the relative approximate error in absolute value is 8.66586. So, and then third iteration, so ganun pa rin yung pag-move ng value natin. So xi should be the new value of xi plus 1. Xi minus 1 should be the latest value of xi. Compute for the values of the function for the new values of xi and xi minus 1 to come out now with 0.5671 as the value of xi plus 1. The value of EA is still 0.58 or 59%, higher than 0.5 if our stopping criterion is set as n is equal to 2. So maybe another iteration to be considered, and we already arrive a value of 0.567 as the value of the estimate root xi plus 1 with a value of relative approximate error in absolute value equal to 0.00477. So that is the solution. Okay, so now kitain tayo. The step to be done here is the same in the Newton-Raphson. The only difference is we have two initial guesses. Okay, so in the computation of EA, the present value natin should be xi plus 1 and the previous value should be xi minus 1. So yung value natin na 63.21 should be solved using the values now under xi plus 1 and xi minus 1. So that is 0.6127 minus 1 divided by 0.6127 absolute value times 100 to come out with 63%. Okay, so and that is for the second method, and those are the two methods under the open method of solving the rules of algebraic and non-algebraic equations or transcendental equations. Okay, so question.